The world is full of secrets, always has been. Knowledge is power. Over the years, many methods have been used to hide information from prying eyes. These methods generally turn encryption into unreadable code. That's all cryptography is, the art of writing or solving of codes. In cryptography, information is changed into an unreadable format. It can't be read by anyone but the intended receiver. The receiver will have a key in the form of instructions of how to unscramble the information and reveal the message. Oops, sorry. The world is also full of curiosity. People who want to uncover secrets, the thirst of knowledge, political advantage, and the thing that sadly makes the world go round, money. For many of you, I imagine a specific word came to mind when I said about these curious people. Hackers. What can we do about them? Well, as there are people out there looking to uncover these hidden messages, the security industry needs to involve the encryption methods they used as they become vulnerable to exploitation. We're at the beginning of a significant evolution in cryptography, one for the history books. We need to get ready for the quantum world. There are two traditional types of encryption, symmetric and asymmetric. Asymmetric encryption uses one key to decrypt and the same key to encrypt data. Asymmetric encryption uses different keys to encrypt and decrypt information. And one I'll talk about today later on, quantum, which is slightly different. So as I just mentioned, symmetric encryption uses the same one key to decrypt and encrypt information. This requires something called a key exchange, resulting in both individuals having the means to encrypt and decrypt messages to one another. The key turns the information into an unreadable format so that it can then be transmitted, and then when received can be unscrambled to reveal the message that was initially sent. There are two types of symmetric encryption. Algorithms, there are two types of symmetric encryption algorithms. Block algorithms, where information is sent in blocks and held in memory until it's all been delivered, where it is then decrypted, and streams, where data is sent in streams and it is decrypted as it is delivered. Symmetric encryption has been replaced by asymmetric cryptography in many scenarios. However, it's still used for payment transactions, proving the sender of a message is who they say they are, and random number generating. The encryption can be tracked back to the Roman era, where Julius Caesar used to send his secret messages using a cipher. The Caesar cipher is a shift cipher, whereby each digit in the message is shifted by a set number in a set direction. This is the key. So you send the information, and then separate to that information, you let the recipient know this is how you decrypt the information. So with this cipher, as you can see, the places, the alphabetical letters are changing. So a shift of 2 would mean, well, a shift of 2 in 4 directions would mean that my name, Jenny, would have J become L, E become G, N become P, and again, N become P, and finally, Y would become A, as it would go around the cipher. There's one thing to note here. This doesn't solve any issues with cracking, as if you have 2 letters that are identical, you will know in this. However, there are methods which will change letters to different letters, even if they are the same. So Jenny would become LGPPA, not really sure how I'd say that. And to decrypt, you just go back the opposite way, 2 letters backwards. So I'm going to talk about a second example of symmetric encryption, which I'm sure a lot of you have already heard about, the Enigma machine. It was used by Germans to send secret messages during World War II. It used a method of encryption called polyalphabetic substitution cipher. This is a cipher which uses multiple alphabets, where one letter is substituted for another letter, which is then substituted for another, and so on. Here's a diagram that depicts that quite nicely. It's very complicated, and for the time it was created, very impressive. So I'm sure a lot of you who are aware of what happened are thinking, but we managed to crack that. Well, we as Britain managed to crack that with help, with the Polish. So the bomb machine was built to crack the Enigma code. It followed up on the work of Polish mathematicians and was successfully created by Alan Turing and his fellow codebreaker Gordon Welchman at Bletchley Park. Bombs were 7 foot wide, 6 foot 6 tall, and weighed a literal ton. The Turing bomb was made up of the equivalent of 36 Enigma machines. It mimicked the exact internal wiring of the German Enigma. It worked by checking almost 20,000 possible positions before finding a match for each letter. During World War II, 211 bomb machines were made and used at the same time, non-stop to attempt to crack the German's code. And throughout that time, other machines, sorry, I forgot the name of them, were actually converted into bombs to aid with the decryption. So the difference between the British bomb and the Polish bomber, I think, is that it had one addition. It used human logic. Using common sense, the team at Bletchley Park were able to figure out a way to make the computations much, much faster. This was that when a letter is encrypted, it would never be encrypted to become itself. And by taking that into account, computations became much, much faster. Another thing is that if there's a set phrase or a set word that happens multiple times a day or even in every message, then that could be used to make the machine much faster. And the one that Bletchley Park used was Heil Hitler. Every message was signed off with Heil Hitler, and by taking this into account, Bletchley Park were able to crack the code. So, asymmetric encryption uses 2 different keys, one private and one public. It came about as a solution to the issues associated with key exchange. Key exchange can be difficult, insecure, and even impossible. So, I was looking for visualizations for this, and I quite liked the one of a toilet paper becoming unraveled. So it's quite easy to unravel the toilet paper, but can you imagine trying to roll that back up to be exactly how it was before? It's almost impossible. And that's how asymmetrical encryption works. It uses the mathematical theories behind prime numbers to create not identical but mathematically related public and private keys that could be used as a pair to encrypt and decrypt information.
One common encryption method that I actually used yesterday in my first session at uni, I had to set up an SSH key for my GitLab account at uni, and I used RSA to do that. So it's currently used, and I'll go on to the future of that later on. But the RSA algorithm uses the premise that it's difficult to factorize a large number to keep information secure. When generating a key pair, two numbers, where one number is a multiplication of two large primes, when generating a key pair, two numbers where one is the multiplication of two large primes multiplied together to create the public key, and the same two prime numbers are used to create the private key. Linear computers would take years to factorize a large number, meaning that this method of encryption is incredibly secure currently. DigiCert estimated that it would take longer than the age of the universe so far to break a DigiCert 2048-bit SSL certificate, which uses RSA. They estimated the universe to be over 13.76 billion years old. And they estimated that it would take longer than that again to break this encryption. But what if there was a way to factorize large numbers that was faster than this? Much faster. I'll come on to that later. First, I want to talk about elliptic curve cryptography. Unlike RSA, I'm not actually sure when it comes to the maths behind this. I've been trying to read up on it, and I'm struggling to get my head around it. I'm going to be honest about that. But what I can say is that elliptic curve cryptography relies on the basis of and this is a quote, difficulty of computing discrete logarithms in groups of points of an elliptic curve defined over a finite field. And that quote is from Microsoft Cloud blogs. So, similar to RSA, where it's difficult to factorize large numbers, it's also difficult to do that. But once again, what if I told you, that there was a way to unravel that would take much less time? Well, soon there will be. This brings me on to quantum computers. First of all, what is a quantum computer? A quantum computer is a computer which stores information using the quantum states of subatomic particles. They're going to make so many changes to the world as we know it. They're going to revolutionize, well, first of all, they're going to break security, then they're going to rebuild security. They're going to change how banking works. They're going to change how conversion of money works. It's going to affect the stocks. Everything is going to be affected by this change. All we can do is try to be ready and take advantage of the advantages it brings. So a quantum computer stores data in qubits, which is the equivalent of a linear computer's bit. These qubits represent a 1 or 0, depending on their quantum property. These could be polarization, phase, or position. Matter acts differently in the quantum level. Due to a phenomenon called superposition, qubits can denote 1 and 0 simultaneously. This could be visualized as a penny on its edge side, not on heads or tails. On a graph with 1 and 0 on the axes, so I might actually draw this. So if I put 1 there and 0 there, this line by here is a vector of 1 and 0. So that would be how you would mathematically denote superposition. is a vector of the two, just like speed and direction, God, this is difficult to write, is velocity. And it can be quite difficult to get your head around vectors. So visualizing them in this way can really help. Another visualization that I'm sure a lot of you know about is Schrödinger's cat. Erwin Schrödinger devised a hypothetical experiment in 1935 where a cat is sealed in a box with a vial of poison, a hammer, a radioactive sample, and a Geiger counter. A Geiger counter measures radioactivity levels, for those of you who aren't aware. So the radioactive material has a 50-50 chance of setting off the Geiger counter in an hour. So should it be detected, the hammer would fall, break the vial of poison and kill the cat. So without opening the box, it's impossible to know if the cat is alive or dead. So this is another different way to visualize superposition. The ironic thing is that Schrödinger actually created this to prove that a cat can't be in superposition. However, his experiment, I hope he didn't actually do the experiment, is theoretical, but this is being used worldwide to explain superposition. So, another vector in the quantum world is space-time. So, space-time is a mathematical model which fuses the 3 dimensions of space and the 1 dimension of time into a 4-dimensional model of space-time. It sounds impossible. Sounds like something out of Star Trek? Well, yeah, but if you look at some modern inventions, mobile phones, tablets, touch screens, they were all on Star Trek before they became real life. And the creator of the phenomenon, the Alcubierre drive, actually was inspired by Star Trek. So, what is the Alcubierre drive? The Alcubierre drive is mathematical proof that it's possible, or could be possible, to travel beyond the speed of light. But in a different way, because it isn't actually the entity that is traveling, but space-time moving around the entity. The entity gets put in something called a warp bubble, and the space ahead of the spacecraft would contract while the space behind it expands. It's essentially the matter of the universe moving and not the spacecraft itself. This means that in the future, if this is actually possible, spacecraft could be used that can ride the universe like a wave. So what does this have to do with my talk? To me, everything. Because I understood space-time before I understood superposition. It's a perfect example of how matter acts differently in quantum space, and it really helped with my understanding of superposition as vectors that can be difficult to imagine. So if this helps any of you understand vectors better, then great. If not, I'm sure this slide has been interesting enough that you don't mind the detour from quantum computing. So, the phenomenon of entanglement binds the density of a quantity of different particles together. This means that something that happens to one will affect all the others. So while a linear computer iterates through sums until they get a success, quantum computers consider all permutations of all possible numbers at the same time. So how does this affect current encryption methods? And just to shout out here, I'm not trying to say I'm a physicist. I love physics, but I don't understand the maths and physics behind these perfectly. So I'm not going to try and pretend I do. I'm going to give my best shot to help you understand it. So SCHR's algorithm uses entanglement to break RSA and ECC fast. A lot faster than a linear computer would. And one thing that's happening at the moment is that quantum computers aren't posing a threat to future information that's stored, but information that is currently stored, because storing information is relatively cheap at the moment. So different governments might be stockpiling encrypted data from other governments to save and decrypt at a later date. And that's quite dangerous. So this is why people need to start acting now on making sure that encryption methods are secure. But how are we supposed to do that? Well, I'll come on to that later. So, similarly to SCHR's algorithm, GROVER'S algorithm also uses entanglement theory to crack security. However, this one is with hashing. It's going to take a lot more powerful computer to crack hashing than it will do for RSA, but it is still possible with a powerful enough quantum computer. This means that while in the next couple of tens of years, we're going to need to start worrying about encrypting data with asymmetrical encryption, while we don't really need to worry about hashing just yet. So, how are cryptocurrencies going to be affected? A lot of people are thinking about this issue in the wrong way. People are thinking that they're going to affect the anonymity of information, of senders and receivers. However, it's not going to affect that at all. Correct me if I'm wrong on that. I'd love someone to explain to me. So, cryptocurrency, as I imagine a lot of you know, uses crypto wallets, and these are protected by public-private key encryption, aka asymmetrical encryption. And they're protected by asymmetrical encryption, which means that with the introduction of quantum computing, they will become vulnerable to exploitation. So this means that it will be possible for hackers to access people's crypto wallets and make unauthorized transactions, which then won't actually be able to be tracked or traced back, and the money won't be able to be retrieved. So the whole idea of crypto being anonymous, that still remains the same. It's just how we protect the crypto wallets is what needs to be changed. So for anybody who doesn't understand how cryptocurrency works, and just because I think this is a fantastic video, I'm about to play a video by the BBC that helps explain exactly what cryptocurrencies are.
When you want to buy something normally, using your normal bank card, this is what happens. I give my card details to the shop. The shop asks the bank if I'm good for the money. The bank checks its records to see if I've got enough in my account. If I do, it lets the shop know. It updates its records to show the movement of money from my account to the shop's. Oh, it takes a little trouble. Now, if you wanted to remove the bank from that system, who else would you trust to keep those records and then not alter them or cheat in any way? I wouldn't trust you. I wouldn't trust you. In fact, I wouldn't trust any single person, but I might trust everyone. The idea is you don't have a central record of transactions. Instead, you distribute many, many copies of this ledger around the world. Each owner of each copy records every transaction. So, to buy something using cryptocurrency, I give the shop my details. The shop asks all the bookkeepers if I'm good for the money. The bookkeepers all check their records to see if I have enough. If I do, they tell the shop, and then all update their records to show the movement of money. So there's no way that a forged transaction can make it in. If I try to alter a ledger, it won't match all of the other copies. And it gets rejected. Oh, and one of them, at random, will be given a reward of some newly created cryptocurrency. This is how cryptocurrencies work. And remember, all of these bookkeepers, all of these ledgers, they're not actually people. They're computers. Lots of computers.
So, good video, right? I'm not actually sure if quantum computers will be able to be advantageous to making cryptocurrencies better. That'll be a talk for another time if I manage to research into that. But they need to change just like everything else does when quantum computers come into real-world situations. So, to recap so far, current encryption methods are vulnerable to the possibilities that arise with the development of quantum computing. This means that information secured with asymmetric encryption will become insecure and a different encryption method is needed. The development of quantum computing means that an idea called quantum key distribution should be about by the time encryption methods such as RSA need replacing, thankfully. The Center for Quantum Technologies shared a fantastic YouTube on video. It's a video on YouTube. It doesn't have a sound, but I'm going to play it and talk through it because it perfectly depicts what I'm trying to explain. The BB84, slipped into Star Wars then. The BB84 protocol is a type of quantum key distribution that relies on quantum computing. It uses the quantum property of polarization to create a key that can be used to decrypt and encrypt information. The quantum property polarization is one you should already be familiar with. Think of Polaroid glasses, windscreens on car, and the awkward moment when people buy glasses that are polarized in the opposite way to their car and they can't see anything. So here's the video. Light particles known as photons are emitted polarized by a Polaroid filter. The light is polarized one or two ways, at 0 degrees, which is horizontal from ceiling to sky, and 45 degrees, which is half of a right angle. If the polarizations, Bob's reading from Alice, are the same as the results he's getting from his own, he keeps it. Otherwise, he discards it, and this is how their key is created. This method is secure because of the Heisenberg uncertainty principle, which states it is impossible to measure both the position and the momentum of a quantum state exactly. This means that while Alice and Bob know which results to remove, Eve does not. Also, by attempting to read the quantum state of the photon, the eavesdropper would actually change the state of it, meaning that there would be a random error in the message. This error would let Bob know that someone had attempted to eavesdrop on his and Alice's data transmission. If the message is still readable with the errors, then there is no need to rerun the quantum key generator. If it is unreadable, the process would be repeated and the data would be encrypted and sent again. So, where are we currently with quantum computing? It can all sound quite scary that there is a possibility to decrypt the algorithms we're using at the moment to keep all our private information secure. And other than the fact that governments are stockpiling data to encrypt it at a later date, most of us don't really have to worry about that. And we can change with the time when the time comes around. The idea is that with the evolution of quantum computing, as the quantum computers become more powerful, quantum key cryptography will become more possible, and it will replace the current algorithms. So this really shows that we don't really have anything to worry at the moment. We would need 6,680 qubits to use Grover's algorithm to break AES 256. At the moment, IBM has, I think, a 20-bit machine, and they're testing a 50-bit machine, 20-qubit machine, and they're testing a 50-qubit machine. Intel has a 49-qubit machine, and Google has a 72-qubit machine. So we're quite far off, and we're actually quite ahead because we already know what we need to replace these asymmetrical encryption algorithms with. It's actually going to take probably decades to need to start using quantum key distribution. But don't quote me on that because that's an estimate. So, while the industry doesn't have to worry about switching over to quantum cryptography for at least 10 years, according to the register, 10 years isn't a large amount of time in tech. One thing I've noticed about the tech industry is that people fall in love with technology from the past, and they struggle to let go, despite maintenance and security issues this may cause. The change to quantum is one of the most significant changes in the history of technology. Well, that's in my eyes, and it's one that we can't ignore. It's going to break everything we know and understand, and we're going to have to relearn physics, rewrite code, and re-encrypt information that we thought was secure. Resistant change is futile, and once we enter the quantum age, prime number-based encryption methods will be too. The 21st century is when everything changes, and we have to be ready. Welcome to the quantum age. So, I decided to do this talk because I absolutely love this topic, not because I know what I'm talking about, and not because I had any idea how to put the talk together. So, why did I do this talk? I want to learn more about it, and by showing other people what I know, they can question what I'm saying and even prove me wrong, and they can teach me. I can share what I know and hopefully teach others. And thought-provoking is good. Bringing something different to the table is good. I'd like to think that, well, I think differently to a lot of people, and I feel that that gives me a bit of an edge. I might be able to understand some of the principles mentioned in this, but I have the least common sense that you'll ever see in a person, and that's what makes me me. So I actually only have a couple more slides, and cut a bit short. I think I'm coming up to 40 minutes. So I could improvise a bit, I could take a few questions. Anyone want to?
Oh, hi Jenny. I was just wondering what you think about Crown Sterling's view that your iPhone can currently crypto all the things.
Sorry?
I was wondering what your view on Crown Sterling's new time-based quantum cryptography is. Are you aware of Crown Sterling? Okay,
no.
Cool. All right, that's cool.
Do you want to explain it? Okay.
I don't think Dan can explain it either. Anybody else have a question?
Make Jamie ask a question.
You're okay.
Am I okay to finish early? Okay, so it's okay to do a quick close? So I want to say thanks so much for listening to this talk. It's actually, apart from a 5-minute talk I did at PyCon 2 weeks ago because I knew I was doing this today, it's actually my first talk. So I hope it's been good, I hope it's been informative, and I know I've been reading from my notes a lot and I apologise for that. But I just guess it's something to learn from and bring on next year, hopefully. Thank you.
Thanks, Jenny. Congratulations on your first talk.